Okay, so I remind you that we have started during the previous session. We have started the following proof. So my first objective today is to prove that the no arbitrage hypothesis seems to work. The no arbitrage hypothesis is equivalent to the fact that the set of the equivalent martingale measure is not empty. Okay? Okay. So I have started the proof, and for the moment we have proved two things. So the first ID, it was the aim of the lemma 5. So we have already seen that NA is equivalent to calligraphic A intersected with L0 plus is reduced to 0. Here you have the final value of the self-finance strategy starting from 0. If they are positive, okay, there has to be 0 if I want the NA hypothesis. Okay? And in the lemma 5, we have proved that in fact this intersection is equivalent to the fact that calligraphic K intersected with delta is empty, where delta is the set of the positive random variable with an expectation equal to 1. So I have this, okay? And what we have seen together is that delta is convex and compact, and we have proved previously that calligraphic A was convex because it is a vector space, okay, and also closed in finite dimension. And we are typically, since I have an intersection that is empty, we are typically in the framework of the convex separation theorem. Okay? So if NA is fulfilled, then this intersection is empty. And according to the reminder I have done on the convex separation theorem, I can say that there exists phi that is linear and continuous from the set of all the random variables with values in R, such that there exists also an alpha belonging to R with phi of k strictly less than alpha for all k belonging to calligraphic k, and phi of y strictly greater than alpha for all y belonging to delta. Okay? The meaning of this one is just the fact that I have two closed and convex sets, one of them being compact. I am able to separate them, okay, through an affine hyperplane. Okay? But I have also said that a linear and continuous form in my framework, okay, as in fact may be written on in a very particular form. Phi as the form phi of x equal to the expectation under P of z x. Right, some things that I have done previously. Just the fact that the linear and continuous form in my setting, okay, may be written as a weighted expectation, okay, with my weight that is this one. Okay, so is that clear for everybody? It's what we have done previously, and I have finished with this one. Okay, so we are going to continue the proof, okay? And this one was the lemma 6. Okay, so I continue my proof. Lemma 7, that would be based on what we have done here. So what is the meaning of this one? There exists Z belonging to L0 of omega Fp. That is the Z given by this expression here, such that what, okay, for all k belonging to calligraphic k, the expectation under P of Z k is equal to 0, and for all W belonging to omega, Z of W is strictly positive. So I have to prove two things, okay, that there exists a Z such that the expectation of Zk is 0 for any k in calligraphic k, and such that Z is always strictly positive. Keep in mind that what I have in mind is to find an equivalent martingale measure. Before to find an equivalent martingale measure, okay, we are going to exhibit a probability, in fact, and this probability will come from the convex separation theorem. By this representation theorem, I obtain in something that is a random variable or a vector with a number of components that is the number of elements in omega. But this vector doesn't define a probability. The first thing I have to check is that all the terms are positive and even strictly positive. So it's what we are going to do. So if I come back to the lemma 6, okay, I can say the following. So it's the proof of lemma. From lemma 6, I just copy what we are writing here. There exists Z belonging to L0 omega Fp, such that what? Such that I have this one. Okay? There exists alpha belonging to R with the expectation under P of Zk strictly less than alpha for all k belonging to calligraphic k, and the expectation under P of Zy strictly greater than alpha for all y belonging to the Z. And what I have copied here is just what I have written in this board. Okay? Now I just have to check that the Z defined this way fulfills the two conditions I want. Okay, for the moment I don't have this, I only have this one. So I erase this part. May I erase this one? Okay. So first thing, if I define this mapping here, that is a mapping from calligraphic K into R, that associate to any element in calligraphic K the expectation under P of Z K. What can you say about this mapping? What can I say about this mapping? Well, first, if I have a look on this one, I can say that this mapping is bounded, okay, by alpha. Alpha is bounded by phi is bounded by alpha. Okay, it's a consequence of what I have written here. Okay. do you have in mind another property for phi here? Yeah, I have something that is linear, huh? Using the linearity of the expectation simply. Phi is linear and defined on the vector space calligraphic K. So what can you say about a mapping that is linear and bounded? It's not false, but we have more and more than this, in fact. Here you just use, okay, the continuity and the fact that I am bounded, okay? Do you know a lot of linear mappings that are bounded? Not that bad, but I can be a little bit more precise. Which constant? 0. I don't have the choice. If I am constant as a linear mapping, since my value at 0 is 0, the constant is 0. Okay? I said that since I am linear and bounded, phi is equal to 0. Do you remind why? Because you can have dilatation, in fact, for linear mappings. Okay? What is the argument of this one? If you have a phi of k0 that is different from 0, okay? So suppose that you are not 0. I have an image that is not 0. By linearity, I have this one where this element here belongs to calligraphic K because calligraphic K is a vector space. And making m lambda, goes to plus infinity, I have a contradiction with the fact that I am bounded. Okay? So bounded for a linear mapping means equal to 0. I don't have the choice. Okay? So phi is equal to 0, and so I have this one. Okay? Necessarily. So for all k belonging to calligraphic K, the expectation under P of zk is equal to 0. Okay? So the only thing it remains to prove here is the fact that Z take only strictly positive values. And of course, if you have understood, to prove that I have the first, I have used this one. To prove the other one, we are going to use the last. The last consequence from the convex separation theorem. So are you okay with this? Yeah? Everybody? So my job now is to prove this one. Okay? We are going to prove it using this. Okay? First remark. I know that K or 0 belongs to calligraphic K because 0 is a vector space. So calligraphic K is a vector space, so 0 is inside. And so if I plug this element here, okay, I have the right to do. This implies that alpha is strictly positive. Because if I take K equal to 0 here, I obtain alpha strictly positive. So I have that for all y belonging to delta, the expectation under P of z delta, zy, is in fact strictly greater than alpha, that is strictly positive. Okay? And now the idea is to use a good choice for y in order to obtain what I want. So remind the definition of delta. Delta is the set of the positive random variable with an expectation equal to 1. Okay? So the idea is to do a good choice for small y in order to obtain this condition here from what I have written here. Okay? Do you have an idea? In fact, I want to restrict this expectation to something that is just related to a particular value of z. For example, if I want to make appear here a particular value for z, I can take y of w equal to the indicator function of w0, w for a fixed w0 belonging to omega. If I put the indicator function, I will have here z of w0. So is y in delta? So that if I want to plug y inside my relation here, I need to check that y is in delta. Is y in delta? In delta, I have positive random variable, so small y is positive, okay, but with an expectation equal to 1. It's not the case. But what can I do in order to have an expectation equal to 1? What is the expectation of this one? It's just the probability of w0. So if I divide by the probability of w0, you have y that belongs to delta, okay? And so I have the right to use this relation. And if I plug inside, I obtain what? So this relation here, this inequality, gives me z of w0 that is strictly positive. That is exactly what I want to have. I have proved this for any w0 in omega. So I know that there exists a random variable that is always strictly positive, and such that the expectation under P of zk is 0 for any k in calligraphic k. Do you agree with what I have written? Yeah? But I deduce from this that alpha is strictly positive. So in the convex separation theorem, you don't know what is the constant related to the affine hyperplane. Okay? But since I have this inequality and since I know that k contains 0, okay, I can plug 0 inside to obtain alpha strictly positive. And it's because calligraphic k is a vector space that I have this one. Okay, so I have what I want. I have proved that there exists a random variable strictly positive, fulfilling this one. Keep in mind that I am looking for a probability equivalent to P. Okay? So I am not very far from what I want. I am not very far from what I want. So I will erase just the beginning of the proof to keep the lemma on the board. Okay, so are you okay with what I have written here? Just basic application of the convex separation theorem. I erase this one here. And if you have understood what I have said, I have a corollary that is a direct consequence of my lemma. Corollary 2. And A implies there exists a probability Q equivalent to P such that for all K belonging to calligraphic K, the expectation under Q of K is equal to 0. I have everything on the board, in fact, for the proof of the corollary 2, it's one line. So Are you able to define me the probability Q? So keep in mind that Z is a vector with strictly positive value. Okay? How to obtain a probability from a vector with strictly positive values? Yeah, the norm if you want, or one particular norm. Okay, the norm 1 in R to the power of the number of elements in omega. So in a simpler way, I can divide by the sum of the coefficient. Okay? So if I consider Z tilde to be Z divided by, so I want to obtain an expectation equal to 1, so I can do, so I want to obtain something equal to 1, so I can do this. Okay? So what I have here for this one? I have that Z tilde is always strictly positive. That of course the expectation under P of Z tilde is equal to 1. So what is the definition of Q I can give? What is the definition of Q I can give? Look at what you want, okay? You want a probability equivalent to P, okay? I have my vector Z with strictly positive coordinates, okay? And I want to transform it in a probability equivalent to Q and to P. What can I do here? Nobody? Well, simply what I have, everything was done to do this. This one. If I do this, since this one is strictly positive, I have Q that is equivalent to P. I have two equivalent probabilities this way. And if you do the sum all the values of Q, you obtain by the fact that the expectation of Z tilde is equal to 1, the fact that you have the probability, the sum of all its values is equal to 1. Okay? So you have here a probability equivalent to P. And what it fulfills, but keep in mind that my Z fulfills this one. Okay, so if I just divide by the expectation under P of Z, I obtain exactly the same thing for Q. And I have the expectation under Q of K is equal to the expectation under P of Z tilde K, that is equal to the expectation under P of Zk divided by the expectation under P of Z. So this is equal to 0. Because I have this. Okay? So you have exactly what you want. If NA is fulfilled, as a consequence of the lemma 7, there exists a probability Q equivalent to P in such a way that the expectation of under Q of any element in calligraphic K is equal to 0. And you are going to see now that if I have a probability equivalent to P that fulfills this one, in fact, it's an equivalent martingale measure. It's an equivalent martingale measure. And we are going to use the definition of calligraphic K in order to prove this. Keep in mind that calligraphic K is what? It's the set of the final values, okay, or discounted final values of self-finance financial strategy starting from 0. Yeah.
So expectation of z tilde under p is equal to 1. Is that by definition, or did you count?
Because I have defined it this way. If you take the expectation under p of this one, okay, by linearity of the expectation, you obtain an expectation equal to 1. This one. If you have a random variable with a finite expectation, if you divide this random variable by its expectation, you obtain at the end something that has an expectation equal to 1 for sure. X divided by expectation of x has an expectation equal to 1 by linearity of the expectation. That's exactly what I do here. No? Just from this one.
When you take the expectation of a fraction, it's
no, it's not a fraction. Okay, you have here a random variable, and here you have a number. So you have, okay, the property of the.
So you can take 1 over
yes.
EPZ
Yeah.
out.
Yeah. 1 over the expectation out because it's a number, it's not a random variable. Okay.
Good. Thanks.
Okay. So now I can prove what I want, that is half of my theorem. Okay? That is the lemma 8. That tells me that NA implies that the set of the equivalent martingale measure is different from the empty set. And of course, the candidate we are going to use in order to prove this will be the Q in the corollary 2 here. It will be this one that will be the equivalent martingale measure. Okay? So before to prove this, okay, if I remind the structure of the proofs, okay, from the convex separation theorem, I exhibit a vector. I prove that this vector is always strictly positive. From this strictly positive vector, I extract a probability that is equivalent to P, fulfilling this condition, and we are going to prove that such a Q is an equivalent martingale measure. Okay? Erase. So what is an equivalent martingale measure? So Q belongs to the set of the equivalent martingale measure, if and only if, by definition of this set of equivalent martingale measure, Q is equivalent to P, and what is the process that is a martingale under Q? The set, the process of the actualized value of the risky assets. Okay, it's this one that is a martingale. Q equivalent to P, and this process was denoted by ST, T belonging to 0, capital T, is a martingale under Q. Okay, and keep in mind that my ST has D components, okay, the D risky assets. Okay. So to prove that the set of the equivalent martingale measure is not empty, in fact, what we are going to do, we are going to prove that this Q here works. That is, if I have this one, I have this one that is an equivalent martingale measure from the fact that it fulfills this condition. Okay. So, what is the meaning of this one? Martingale. You know that when you have a vectorial martingale, it means that any coordinate is a martingale. Okay, so it means that for all D0 belonging to 1D, okay, ST D0 is martingale. But but I am in discrete time. So it means that to say that STD0 is a martingale just means that for all T0 belonging to one, this way. So for all T0 belonging to 0, T minus 1, the conditional expectation under Q or S T0 plus 1 D0 given FT0, okay, has to be equal to S T0 D0. It's the meaning of being a martingale when I am in discrete time here. Okay. And what is the meaning of this one? What is the definition of the conditional expectation? It means that for all A belongings to Ft0, I have the expectation under Q of indicator function of A S T0 plus 1 D0 minus S T0 D0 is equal to what? 0. And you see now that appears the link between what I want and what I have. Okay? So I have this. So for the moment I have written nothing. I just written the definition of what is a vectorial martingale. Okay? So I want to have this. Okay? If I want to have this, but I need to write the variable I am interested in here as an element of K, where calligraphy K is the set of the actualized value of self-finance financial strategy starting from 0. Okay? So what we are going to do, it's not that complicated here. So I need to define a self-finance financial strategy starting from 0 in such a way that its final value is exactly this one. Okay? In order to describe a self-finance financial strategy starting from 0, we have seen together that I just have to describe the quantity of risky assets I have in my portfolio. And what we are going to take as quantity of risky assets in my portfolio at time t equal to 0, I will take the following. So I have HTD that will represent the quantity, yes, of the assets. So how to write it? Okay, by this way, yes. Now write it this way. So the quantity at time t of the ice risky asset, I will take for this one. I will take indicator function of A, indicator function t equal to T0, indicator function I equal to I0. So it means that if I am not I0, so I have 0 for all the risky assets that are not the I01, I do nothing except at time t0, and what I do at time t0, I do the indicator function of A, and in this way I am sure to define a process that is adapted to my filtration. Okay? Keep in mind that the set or the process of risky asset has to be adapted to my filtration, and this is the case here. This is the case because, in fact, I only take into account the time t equal to t0, and I have supposed that A is ft0 measurable. Okay, so adapted because A belongs to ft0. So I have here defined, okay, quantities of risky asset. If I consider H as capital T, I know from the definition of calligraphic K that this belongs to calligraphic K because I am the actualized final value of a self-financed financial strategy starting from 0. But what is this one in this situation? So keep in mind that I start from 0 and I am self-financed. So this is equal to 0 plus the sum of term of this form. The vector hk sk plus 1 minus sk from k equal to 0 to t minus 1. Okay. But what is my h? So here I have a scalar product. But a scalar product where, in fact, only one component is not 0. So my sum here is the sum from k equal to 0 to t minus 1 of, in fact, of what? I can write it this way. H k I0 multiplied by S k I0 plus 1 minus S I0. Because in my vector here I have only one component that is not 0 by this indicator function. So I do the sum from k equal to 0 to t minus 1. Okay, once again, I have only one time where I am not equal to 0, at time t equal to t0. So in fact, in this sum I have a single element that is h t0 I0 s t0 plus 1 I0 minus s t0 I0. And my h t0 I0 is just equal to the indicator function of a s t0 plus 1 I0 minus s t0 I0. And what I have from corollary 2, but I know that this one is in calligraphic K. From corollary 2, I know that the expectation under Q of HS capital T, okay, is equal to 0. What is the meaning of this? It just means from my little computation here that the expectation under Q of the indicator function of A S T0 plus 1 I0 minus S I0 0, this is equal to 0. That is exactly what I want to prove in order to prove that I have a martingale. So the Q defined in the corollary 2 is in fact, from my computation here, an equivalent martingale measure. That is a probability equivalent to P that make the actualized value of the risky asset a martingale under Q. Okay? So I have done the proof of half of the theorem. That is in fact the difficult part of the theorem. That is, if I have the no arbitrage hypothesis, then the set of the equivalent martingale measure is not empty. Okay? And keep in mind that my argument in order to exhibit such a Q was to use the convex separation theorem. I work a little, but the main theoretical result below this proof is the convex separation theorem. Okay? So now it remains to prove by the converse that if there exists an equivalent martingale measure, we are going to prove that NA is fulfilled. Something that is easier and easier to prove. So are you okay with my implication? NA implies the existence of an equivalent martingale measure. Do you have some questions? No? Hmm? Voilà. What I have starting from the fact that I have a queue that fulfills for any k in calligraphic k, the expectation under q of k is 0. It's my starting point. I have said I want to prove that this q is an equivalent martingale measure. So first of all, I have said what is the meaning of being an equivalent martingale measure. To be an equivalent martingale measure means that I am equivalent to P, and such that the actualized value of the risky assets is a martingale under Q. That means exactly this one. So at the end, I have expressed what I want to obtain, that is to be a martingale this way. If I prove this one, I have an equivalent martingale measure. And in the second step, I prove that this one holds. That is exactly what I do. Okay? So I don't suppose what I want to conclude, okay, but I just show that Q is an equivalent martingale measure, proving before that it is sufficient for me to prove this. This is the martingale condition. In fact, it's just the definition of what is a martingale. Some things that you have seen again this year with Bernard de Meyer, I imagine. Okay? Okay? So I have proved that NA implies there exists an equivalent martingale measure. Okay? My job now is to prove the converse. So if you are okay, tell me, I will erase the board if you don't have questions. Okay? And below, I repeat, theoretically, I have the convex separation theorem. And you will see that I will use this theorem 3 or 4 times in this course, okay, when I will want to exhibit someone that is a probability, in fact. It will come from the convex separation theorem. So I erase everything. So now, it remains, if I want to have the proof of my theorem 1, to prove this. If I have an equivalent martingale measure, then NA is fulfilled. Okay? And you will see that it is easier to prove. It will be the consequence of 2 little lemmas. Okay? The lemma 9 and the lemma 10. So it's what I want to prove as a consequence of the 2 following lemmas. So suppose that you have Q in the set of the equivalent martingale measure. Okay, so I know my hypothesis now is that the set of the equivalent martingale measure is not empty. So I take one inside, okay, and I say that if Q belongs to the set of the equivalent martingale measure, for all H belonging to calligraphic HD, that is the set of RD valued stochastic processes that are adapted to my filtration, that represent in fact the quantity of risky asset for a self-finance financial strategy. So for all H belonging to calligraphic HD, then the following process is a martingale under Q. So when I am an equivalent martingale measure, it means that the actualized values of the risky assets are martingales under Q. I said that anytime you are going to build a portfolio with these risky assets, the associated actualized value will be also a martingale under Q. Okay? So keep in mind that what is HST T. It's a sum, okay, of things of this form here. And it's from K equal to 0 to T minus 1. Okay? How to prove this? It's not that complicated to prove this. My hypothesis is that here Sk is a martingale under Q. Okay? If I want to prove that I have a martingale, I am interested in the expectation of under Q, for example, of Hs T plus 1 given Ft. Okay? And I want to prove that this is equal to HST, the definition of a martingale in discrete time. And in general, okay, when you try to compute this kind of expectation, you can try to isolate something that is measurable with respect to Ft and another part and see what you can do. But from this sum here, I see that Hs T plus 1 may be written as HST plus a single term that is just HT ST plus 1 minus ST from the definition of HST. And so I can plug this relation inside my conditional expectation, and in fact I obtain what I want. In fact, by linearity of the conditional expectation, I obtain two terms. The first one being what? Because HST is an adapted process, so it is Ft measurable. So here I simply obtain HST. And for this one, what is the value of this conditional expectation? So for the moment, I don't use the fact that Q is an equivalent martingale measure. Huh? I don't use this. And I need to use it, for sure. So what is this conditional expectation here? 0. Okay. Why it is 0? Because you have here a part that is Ft measurable. So you can remove it from the conditional expectation in order to obtain, I can write it this way, Ht conditional expectation under Q of St plus 1 minus St given Ft. Okay? Using the fact that I can remove from the conditional expectation things that are Ft measurable. Okay? And what I have inside here, my 0, because Q is an equivalent martingale measure. Okay? So it means that the actualized value of the risky assets is a martingale under Q, and so my conditional expectation here is reduced to 0. Okay? So when you have an equivalent martingale measure, if you consider the self-finance portfolio, then you are sure that the actualized value of this self-finance portfolio will be a martingale under this equivalent martingale measure. What you have for the values of the assets will be transmitted to the values of any self-financed portfolio. Okay? So I have this, and in fact, if I have this, it won't be that difficult to obtain what I have, because I know what? I know that the values of a self-financed financial strategy is a martingale. In particular, it is constant in expectation. means that the set of my possible values can't be anything I want. So it's the last part of this one. So I erase here. The proof of my implication here. And if I finish to prove this one, I will have the proof of the theorem wall that will be complete. Before I start to do this, that is not complicated, do you have some question with what I have done here? It's just, okay, basic properties of conditional expectation. Okay, so I have to prove NA. I remind you that NA is equivalent to the fact that if I am the final value of a self-financed financial strategy, and if I am positive, then I have to be equal to 0. Okay? Characterization of the NA hypothesis. We are going to take someone here and prove that it is necessarily equal to 0. Okay? So let J belonging to calligraphic K intersecting with L0 plus. So I have two things. I have the fact that J is positive, P almost surely because it belongs to L0 plus. And I have the fact that J belongs to calligraphic K. Okay? I have that J is in calligraphic K. Can I conclude for the expectation of J under Q? Why? Oh, be careful, huh? Okay. And O, I know that the set of the equivalent martingale measure is not empty. Okay? In fact, I'll try to erase the board first. In order to be more precise here, the set of the equivalent martingale measure is not empty. So there exists at least one. Okay, so consider, let's say, Q0 belonging to the set of the equivalent martingale measure. I have the right because I know that it is not empty. Okay? I said that NA is equivalent to this one, so what I want to prove is that this one is included in 0 because I have the converse, I know this. Okay? So I take an element inside. It is positive for sure, and I said that the expectation under Q0, my Q0 that is here, of J is equal to 0. Why I have this? So be careful, it's not what I have proved in corollary 2. In corollary 2, I have proved that there exists a Q such that for any K in calligraphic K, the expectation under Q of K is equal to 0. But it was for a particular Q, the one I have built. Here, it's an arbitrary Q0 in the set of the equivalent martingale measure. Why this expectation is equal to 0? In fact, you have just to remind what is the meaning to be in K. What is to be in K? To be in K means that I am the final value, the actualized final value of a self-financed financial strategy. It is of a self-financed financial strategy starting from 0. Okay? It is the definition of being in calligraphic K. I am the final value of a self-financed financial strategy starting from 0. But I have proved here that the value, the actualized value process of a self-financed financial strategy is a martingale under any equivalent martingale measure. So, I repeat, you are a self-financed financial strategy starting from 0, and you know that your process of actualized value is a martingale under Q. What can you say about the expectation of your final value, actualized final value? That's 0, because the martingale is constant in expectation. The martingale is constant in expectation, so if you start from 0, the expectation of your final value will also be 0. So this one is because of lemma 9. And a martingale is constant in expectation. If it starts from 0, the expectation of its final value is also 0. So I am in this situation here. Okay. I have something that is positive with an expectation equal to 0. What can you say? So J equal to 0, Q0 almost surely. And in fact, this is also P almost surely because Q0 is equivalent to P. Because Q0 is equivalent to P. So you have what you want. Okay? So we have proved together that in the model we have considered, the NA hypothesis is equivalent to the fact that the set of the equivalent martingale measure is not an empty set. Okay? The second step of the course will be to see what to add to the NA hypothesis to make the set of the equivalent martingale measure a singleton, a single one. Okay? Because in what follows, okay, the prices of the contingent claims we are going to deal with will be conditional expectation of the payoff with respect to an equivalent martingale measure. And if I want to have a kind of unicity of the price, I need that the set of the equivalent martingale measure is reduced to one element. Okay? It's exactly what we are going to do now. Okay? What to add to the NA hypothesis. So NA implies, or in fact equivalent to the set of the equivalent martingale measure is not empty. What to add as an hypothesis in order to make this set a single probability. Okay? Only one. I know that there exists at least one if NA is fulfilling, and I want at most one with an extra hypothesis. That is exactly what we are going to deal with now. Questions? No? So in the second part, the first chapter, so the chapter 0 was, okay, notations and so on. Okay, first chapter, fundamental theorem of asset pricing. Second chapter, what we call complete markets. Okay? And in fact, I will give you the definition in a few seconds, but a complete market is a market for which any contingent claim may be written as the final value of a self-financed financial strategy. And in other words, with what we have defined previously, it means that all the contingent claims are replicable at a particular price. Okay? So if you are okay, I erase everything. Okay? No questions? So I erase, and we are going to start the second part of the course. And once we will have this result, we are going to be able to price in particular situation and even to hedge. It will be the aim of the next session. Okay. So second chapter, complete markets. Okay. It's the definition 9. The financial market is complete if any contingent claim is replicable at some price. In other words, if I use the previous notation I have introduced, okay, I can write it this way. For all u at belongings to L, so infinity omega f p, there exists an A belongings to R, that will be the replication price, okay? There exists an H belongings to the set of the RD valued stochastic processes that are adapted to my filtration, that will represent the quantities of risky assets in my portfolio, such that I want that the final actualized value of the associated financial strategy is exactly equal to the actualized value of U. So such that U equal to A plus H S capital T. And intuitively, for a financial market, the fact to be complete means that, in some sense, you are able to create any kind of possible value from the risky assets. So using portfolio only made of risky assets, you are able to obtain at the end all the contingent claims. Okay, that will represent for us, as I have already said, all the possible payoff, let's say, of European type option, for example. Okay? So you can reproduce all the payoff using only self-financed financial strategy, okay? Made from risky assets. Yeah. I just because here you know that this is the actualized final value, okay, of a self-financed financial strategy. So I want them to be equal. So I write the equality in a discounted way. Yes?
So any payoff of any contingent claim, yes?
Yeah. But for me, contingent claim and payoff, it's the same in fact. Okay? And just mean that if you use only the risky assets, so the D assets you have in the market that you are able to trade, you will be able to obtain at the end, okay, any kind of payoff using only strategy involving the risky assets. Okay, so from these risky assets, you are able to reproduce at capital T any time of payoff, that is any type of contingent claims. Okay? So a little remark concerning the fact that I have written it as a remark, or maybe it's like a corollary or lemma, but whatever. I will write it as a remark to coincide with my lecture's note. But the fact that if I suppose that NA is fulfilled, so if I have no arbitrage hypothesis, and in fact, if you are replicable, the replication price is unique, and in fact, more generally, the value at any time of any replication portfolio is unique. A priori, when you see this definition, there is here, there exists. But maybe I can have several replication strategies, okay? But what we are going to see now tells us that you may have several replication strategies, but in any case, their value at any time will be equal if the no arbitrage hypothesis is fulfilled. Okay? So in other words, it may be a result you know on this form here. If you have two self-financed financial strategies, if they coincide at the end, they coincide everywhere. Another way to say this. Okay? So I write what I have written, what I have said here. Okay? This one. The remark, let's say, with a little proof inside. I don't know what time is it, and probably I will conclude with this one today. Okay? So I have an hypothesis. I suppose that NA is fulfilled. What happens if NA is fulfilled? So I say the following. If U at is replicable at price small a, meaning this one, in fact, I will just copy what I have written in order to erase this one after. So if I am replicable at price small a, meaning this one, then A and the process HST, for T belonging to one capital T, are unique. And more precisely, I can write small a as the expectation under Q of U, and I can write HST as the following: A plus HS small t is equal to the conditional expectation under Q of U given Ft for T belonging to one capital T, and this is true for any Q belonging to the set of the equivalent martingale module. And I know that this set is not empty because I have supposed that NA is fulfilled. So I repeat. If NA is fulfilled, I said the following. If I have a contingent claim that is replicable, meaning that it can be written as the final value of a self-finance portfolio starting from small a here, then small a is unique. And what is more, this process is also unique. Okay? Meaning that the actualized value or the value of any replication portfolio is something that is in fact unique, independently of the fact that I can have several replication portfolios. And what is more, I know the way to compute them. The price is just the expectation under Q of the payoff, the actualized payoff. The actualized value at time t is just the conditional expectation of the actualized payoff given ft. And this is true for any equivalent martingale measure. Okay? It's true for any equivalent martingale measure. Meaning that this one is independent of Q, in fact, this equality. So first of all, before to do the proof, why I have this here? Why I have this? But if you take the expectation under Q of this one, you obtain this one. Because I know that if I am an equivalent martingale measure, it's the last lemma I have proved, okay? The expectation under Q of this one is 0, okay? Because it's the final value of a self-finance financial strategy starting from 0, knowing the fact that the actualized value is a martingale, so it is constant and expectation and equal to 0. And if I start from this one, and if I take the conditional expectation given ft, I obtain exactly this one. Conditional expectation of u given ft is equal to small a, my constant, plus the conditional expectation of this one given f small t, but I know that this process is a martingale under Q if Q is an equivalent martingale measure. So what I have in orange here is just a consequence of the fact that Q is an equivalent martingale measure and of something that I have proved just previously. Okay, so the fact that A is equal to something and that I have this equality is just a consequence of the definition of to be replicable at price A, and I take the expectation and the conditional expectation in order to obtain this one and this one. Are you okay with this? Oui, no? Okay. So I have to prove the unicity. Okay? We are going to prove the unicity of A and the unicity of the process. And of course, how to prove the unicity? I will prove the unicity by the fact that NA is fulfilled. That is, there are no arbitrage opportunity. We are going to suppose first that A is not unique. So suppose that there are two A. And we are going to prove that in this case, I have a contradiction with the fact that NA is fulfilled. That means that I will be able to exhibit an arbitrage opportunity. Exactly the same thing for this one. If we suppose that there are two stochastic processes fulfilling this one, we are going to prove that it is in contradiction with the fact that NA is fulfilled. Okay? So my job now is to try to create arbitrage opportunity if the uniqueness is not fulfilled. Okay? So here I prove that A is unique. We are going to suppose the contrary. Suppose that you can be replicable at two different prices. Okay, so suppose that we don't have the unicity meaning that U can be written as A1 plus H1 S capital T, and may be written as A2 plus H2 S capital T. So I suppose that I have two possible replication price, okay? And I suppose that A1 is different from A2. For example, that A1 is strictly greater than A2. Are you able to exhibit an arbitrage opportunity here? You can describe it to me, let's say financially or purely mathematically. So if you are in this situation, how to win money without taking risk?
You buy the one with H1 with
So you buy H1 with which money you do this? Be careful, huh? An arbitrage opportunity, you start from zero. So you sell which one? So in fact, we short sell, vente à découvert, the most expensive one in order to buy the other one. Okay? So if I am in this situation, we are going to short sell at the short sell at the greatest price in order to buy the other one. Okay? In other words, in order to describe a self-finance financial strategy starting from zero, I just have to describe what is the quantity of risky assets to put in my portfolio. I will short sell this one in order to buy this one, so I have H2T minus H1T. So exactly to short sell this one in order to buy this one. And what I obtain at the end, here, at the end, if I have a look on HS capital T, it is equal to what? It is equal to H2S capital T minus H1S capital T. And what can you say about this one? It's strictly positive because I have supposed A1 strictly greater than A2, and the fact that I have this equality because they are replicable with both strategies here. Okay? So I have H2 minus H1 that is equal to A1 minus A2, so I have something that is strictly positive, and you have here on the board an arbitrage opportunity. So here I do, let's say, the description mathematically, in the sense that I know that in order to describe a self-finance financial strategy starting from zero, I just have to say what are the quantities of risky assets. And I take this one, H2 minus H1. Financially, what does it mean? It means that if I am in this situation, I am able to replicate in two different ways my contingent claim. I suppose that one price is more expensive than the other. I will short sell at this price in order to be able to buy the second strategy. And at the end, I will be able to reimburse and to make a profit because I have this strict inequality here. It's exactly what I do when I do this, but just with my notations. Okay? The minus here means short sale of this one, the most expensive one. Okay? So I have proved the unicity of A. Okay? Questions? No? The last part. So I have proved the unicity of A. What I want to prove now is that this is unique. Question.
En fait, c'était le fait que l'espérance conditionnelle est unique et on a la relation HST est égale à l'espérance conditionnelle moins A, mais on vient de trouver que A est unique, donc les deux sont uniques.
If you do this way. So we have proved that A is unique. Okay, so I have this one, this one. Yeah. But the idea is just to say that, so suppose that I have two of this type here. Okay, so I know that my A is unique. Okay, I have proved it previously. So I have something like this here. Suppose that you have two strategies that works. From this line I have already proved, I can say that I have this that is also equal to A plus H2 ST. And so I have my result. Or the only problem I may have with this proof, that is perfect, very short, it's okay, and I will do this one. But you will see in my lectures note that I have another one that is more constructive. That is, the idea is to build an arbitrage opportunity. What happens if I don't have this unicity? I am able to build an arbitrage opportunity. And I do this concretely. Okay, in order that I detect that I have some problem, I want to be able to take benefit of this one, okay? And I do this. But I am agreed that it works this way. So once I have proved the unicity of A, if I suppose that I am replicable with two different strategies, okay, I know from this one that this one is equal to this one, that is also equal to this one, and so necessarily these two are equal, implying the unicity I want, okay, for unity. Okay. Another way to do the proof, as you will see in the lecture's note, is to suppose that I don't have the unicity, meaning that there exist two that are different. What is to be different for two processes just means that there exists a time where they are different. And from this set, in fact, we are going to be able to build an arbitrage opportunity in this period. If they have different values at some time, I will short sell at the most expensive price. I will buy the other one. I will wait until the end, and at the end I will make profit for sure. Okay? But this is a short proof, and I will conclude by this one. Okay?